say you're looking for CLRS, how do you go about looking for this book in this big library? And usually what we're going to do now is you'll say, well, it's probably alphabetical. You know that it's by Corman is the first one. The C's are kind of towards the beginning of the alphabet. And so I should start somewhere towards the beginning of this library. But of course, if you look inside of CLRS, that's not what CLRS would have you do. CLRS would say, given this sorted array of books, of integers, of whatever the case may be, you should start in the middle. And we're going to do our favorite binary search. We're going to recurse on the right subhalf and on until we find the number, right? Or the book that we're looking for. And the lookup time here, as well known, is logarithmic in the number of elements in the array, right? But what is the process that we actually went through, right? We had a prediction in our head and we said, well, C is towards the beginning, or the number 7 is kind of small compared to what I expect to see. So I'm not going to start in the very middle of the library or of the array. I'm going to start and bias my starting point a little bit more towards the left, right? And so I'm not going to start in the middle. I'm going to start somewhere here. And then I'm going to say, well, it's probably, my guess is pretty good, so it's probably nearby. So I'm not going to recurse on the whole left half of the array, but I'm just going to start looking locally for this number 7. Right, and this is essentially one of the ways to think about the learned index structure paper that really kicked off a lot of the work that I'm going to talk about today. Right, and the analysis here is relatively simple. So if I look at the error in my prediction, so it should have, I should have looked in the 3rd bucket, but I'm looking in the 7th bucket from the very beginning. It's easy to convince yourself that at least the theoretical running time is going to be logarithmic in the length of this L1 error between where I should have looked and where I started looking. Right, and empirically, as Tim went through a lot of detail this morning, this is not just a theoretical improvement. We do see a lot of performance wins if you tune these kind of systems correctly. Right, so we can go back and we say, well, there's 2 running times that we can compare. The classical one is logarithmic in the number of elements. The predictions one here is logarithmic in the error. And unless you're doing something completely and utterly ridiculous, the error is bounded by the number of elements that you have. And so this kind of algorithm here has these 2 really nice properties that if the predictions are good, they're nearly optimal or they're perfect, you recover a constant lookup times, which is as good as it gets. But it's also robust to the error in the predictions. And this is a discussion that we just had with David's talk, that even if the predictions here are bad, you're obviously going to be slightly worse in the classical approach, but you're not going to be much worse. In particular here, you just lose a constant, right? And so what we've done here, the punchline of all of this is that we're tying the performance of the algorithm. And here the performance is on running time, but we can see going to other directions as well, to the quality of the prediction that you have, right? And so the better, the more predictable the input or the better machine learning system that you can come up with, it actually improves the overall performance of what we're trying to do in kind of algorithms 101. Right? And this has had a lot of success in theory, especially in applications to online and streaming algorithms, right? We can talk about caching and predicting which elements to evict and generalizing that to weighted caching, metrical task systems, et cetera. We can talk about sort of really basic problems like ski rentals. We can look at the whole field of scheduling, online learning. We talked about heavy hitters and other stream-based predictions, right? And for a lot of these, this is a natural fit because both in online algorithms and to some extent in streaming algorithms, the predictions help you battle against this future uncertainty, and they help you constrain the problem space and steer you away from worst case instances. And that gives you these performance wins that we have seen, right? And that we're going to see, I think, in the next couple of talks as well. But the question that I want to go back to today is, what about the original question of speeding up algorithms, right? And so Tim has talked about this morning with regards to data structures, to say, well, we have learned indices, maybe there are multidimensional indices, they can go in a number of different directions. What else can we do? What other algorithms can we go after and say, here's a faster version of what you have? So this is what I'm going to talk about for the rest of the talk. And the key observation here is that in practice especially, it's rare that you run an algorithm once, right? So it's usually that you have some algorithm and many of these problems are solved repeatedly day after day, right? So if you think about your scheduling problem, and I think David mentioned this as well, you get some number of jobs to schedule to machines today. You're going to get jobs to schedule to machines tomorrow. And lo and behold, some of these jobs are just jobs that happen nightly. Your backup jobs or something else that you're updating some index somewhere or something else. And yet, even though these things happen almost every day, more or less, we're like Dory. We have no memory. And we say, oh, look, a job showed up. I don't know where I should put it. Let's try to allocate it to this machine. Oh, look, another big job showed up. I don't know where I should put it. Maybe I should randomize. Maybe I should do something else. And so at least the algorithm principles that we teach say that we should start solving from scratch every single time, right? And so the question is, how do we use the memory that we have, right? And so if we say, these jobs tend to show up, these kinds of constraints tend to show up, this kind of flow tends to show up, and so on and so forth, how do we use this to improve our algorithm design and to improve the allocations and to improve the speed? So if you go and you talk to people who do this for a living, they'll say, well, nobody really starts this from scratch. That would be ridiculous. And so we employ what's known as warm start, right? And what warm starts attempts to do is at least to say, I'm going to start somewhere close to the solution that I expect. And then I'm going to run some iterative procedure to really hone in on the optimal solution that I'm looking for. And the fact that I'm starting not from the beginning, kind of an all zeros vector, if you will, allows me to actually do this significantly faster because I've already taken some of the obvious steps that you are going to do anyway, right? And in the library example, this just says, the warm start is I'm going to start looking in the beginning instead of recursing from the middle of the array. So warm start is something that is used left and right every day. But if you start digging for formal analysis of what does warm start mean and how well does this work, relatively little is known. So the goal for today is to actually tie tie predictions into warm start and put it on a solid, rigorous foundation. So let's see how we get there. So the high level setup here, just for a little bit of notation, is to say we're going to see a number of problem instances, x1, x2, and so on, that are drawn from some unknown distribution script D, right? And this allows us to say that whatever solution that we're going to have is going to generalize to future instances overall. And our goal is twofold. We simultaneously want to identify something that's going to serve as a summary for this warm start. It might be a sub-solution or it might be something else, some other structure. And we want to design an algorithm that when given this warm start summary on instances that are drawn together with an instance that's drawn from this distribution, it runs faster in expectation than something that doesn't have this summary at all. Right. Great. So what are the things that we're going to look for, right? There's kind of three different directions that we need to hit. One is, what is this warm start solution S? It might be, is it even feasible for the instance that I have? If it's a sub-solution, how do I wrangle it to make it something that's useful? The second one is, how do I actually use it? So I have this warm start solution. It's a solution to some other problem or to some other subset of problems. How do I then actually use it in my algorithm design to get something faster in the end? And the last one is, I think a lot of folks yesterday focused on this, is to say, how do I make sure that it actually does generalize to unknown and new instances? And formally, what this means for us is that how do I make sure that it's pack learnable, right, overall? And the tricky and the interesting part here is that I need all three. If I'm missing any one of these three pieces, then the whole framework kind of falls apart. If I have something and my warm start is not feasible and I don't know how to make it feasible, then I don't know what to do with it. If it doesn't actually help me optimize, then it's also not very useful. And again, if I can't learn it from a small number of samples, then it's not something that's going to be successful and useful to me overall, right? If I need thousands upon thousands of samples to learn a warm start solution, and I just get one sample, one problem instance per day, I have to wait years, literally, before I get something that I can do something with. Right. Good. Any questions so far?
Can I ask you a question?
Please.
So here you seem to constrain yourself for a warm start to be one element of the solution space. We could think of many other ways to warm start an algorithm. For example, you could get a sampler, you could get, I don't know, some other modifications that you could add onto your algorithm. So you're going to be working under this constraint throughout?
So for the instance here, so now we're gonna move on to matchings and sort of say for matchings in particular, how does this work? It's going to be a sub-solution, but the point that you're making definitely stands, that it doesn't need to be something like this. It could be some other way of approaching and getting some handle on what the future is gonna look like.
All right, thank you.
Other questions? Cool. Okay, so let's think about matchings. I'm going to say, you know, we've covered data structures with indexing. What is our simplest or one of the most native primitives? And that's matchings, right? And in particular, I'm going to look at minimum cost bipartite matchings and go from there. So what is it? Just that so we're on the same page. You're given a bipartite graph, G, with the left-hand side and right-hand side and weighted edges between them. The edges have costs that I'm going to denote by Cij. And I need a sense of scale here, right? So if I multiply all the costs by a factor of 2, nothing really changes with respect to the combinatorics of the problem. So I'm going to say, let's say there's a maximum cost and a minimum cost, and the capital C is the scale parameter of the 2. And my goal is to find the minimum cost perfect matching. So every node on the left is matched with every node on the right. And I sum up the cost of the edge cost in the matching, and I want to minimize this. Right. What is known about this set of problems? There's a very rich literature. This slide is not going to do its summary, but this is kind of all that we're going to need for today. So if you're doing unweighted, so if all of the costs are uniform, then all you're really trying to find is the maximum cardinality matching. You're trying to find a matching with the maximum number of edges, and then you can tell, is it a perfect matching or not? And here the running time is roughly order m square root n, is what you can get to. Right? Now, if we say no, the costs are important, and so we have weighted instances, there's two approaches that you can take. You can go sort of very classical and old, and this is the Hungarian algorithm that uses max cardinality matching as a subroutine and does it about square root n number of times, number of rounds. Or you can take the latest and greatest that does a lot of different algorithmic tricks to get to the lowest possible running time. And then on top of this m root n, you have a log c, where c is the scale parameter factor on top of it. Right? So the Hungarian algorithm is easy. It's implemented left and right. You can implement it yourself. It's not going to take you that long. The state of the art, of course, gives you a much better theoretical running time, but requires some work to do. And it's not clear where the trade-off between the theory and the practice would come in. Right? Good. So what do we want to do? Right? We want to say, what is actually, so this is the problem that I'm going to have. Day after day, somebody comes to me and says, Sergei, here's a graph. Here's the left-hand side, here's the right-hand side, maybe the nodes stay the same. Here's a new set of edges, right? Find me the min cost perfect matching with this new set of edges. Tomorrow, another set of edges arrives. Friday, another set of edges arrives, and so on and so forth. Right? So the first thing that you might want to do is you want to say, well, I'm going to use the set of edges in the optimal solution, let's say from yesterday, or from some combination of optimal solutions over the past week, as my warm start solution. And so I'm going to say, hey, here's a particular submatching, and let's start with this submatching when we go forward. Now, this is not a formal statement, but if you start thinking about this direction, this set of edges appears quite brittle in that I can change the instance weight and its weights in a very small fashion. And this primal solution, the set of edges that I'm going to have, in the optimal solution changes quite drastically. Right? And so this, at least intuitively, makes you question whether this is the right way to start or to warm up a max weight perfect matching algorithm. So instead, what we're going to turn to is that we're going to turn to LP duality. And for matchings, this is not, we're definitely not the first ones to turn to duality to think about how do you handle matchings with predictions. This is relatively well studied in the online matching community, especially in kind of matching users to advertisers in AdWords style settings and matchings. But they're concerned, again, with improving the competitive ratio and making the algorithm give you a higher quality result. Here, we care about speed. Okay, so just to, again, to write this down. So we have the primal here on the left. What does the primal tell you to do? It says, well, we're trying to minimize the cost of the matchings, subject to the fact that every node is matched. Right? This is all that the left-hand side primal says. And now what is the dual version here? The dual version says I'm going to assign prices, which I'm going to call yi's, to vertices. I want to maximize the total value of prices, but I have some constraints in that for any particular edge, the sum of the prices of its endpoints can be no more than the value of this edge, right? No more than the cost of this edge. And so I can't set all of the yi's to infinity. They're capped from above. And so the question is, how do I decide for a particular edge? You know, if I have a edge of weight 10, I can split it equally and say that the prices are 5 and 5 on both sides, or maybe it's 9 and 1, or maybe it's 8 and 2. And this is the combinatorial optimization that I have to do in order to maximize the dual. Right? So I'm assigning prices to vertices, and every edge is going to upper bound the sum of the prices that I have. And let's recall, again, complementary slackness for optimality. What is this going to tell us? That edges in the matching have the tight dual constraint. So for the edges that are actually present in the matching, for them, the sum of the shadow prices here is going to exactly equal the cost of the edge. Okay. So far, so good. So how does the Hungarian method work? Because this is what we're going to be working with most of the time, is we start with dual values at 0. So I said all of the yi's at 0. This is feasible for the dual. I can compute the max cardinality matching on the tight dual edges, right? On the edges where the edge weight is exactly equal to the sum of the shadow prices of its vertices. And either this is a perfect matching, in which case I'm done, or it's not a perfect matching, and now I need to update the dual. So I'm going to increase the yi's in a particular manner. And now I've increased the yi's, I've made some progress, and now I'm just going to repeat. I again compute the max cardinality matching on the tight edges. If I'm not done, I find some violating set, and I repeat, and I keep on going on. And this is why the running time of the Hungarian method can be expressed as the number of iterations, the number of rounds of this max cardinality matching as a subroutine. Right? Right. So now what are we going to do? Now, if we think about this algorithm and say, how do you warm start this? You can say, well, Sergei, this is really easy to warm start. The idea is obvious. You shouldn't start with yi's starting at 0. You should start with yi's starting at something. Right? And this is exactly what we're going to do. We're going to say, let us predict these dual values. So they're going to be the y hats. The hats give you the predictions. And now I'm going to warm start this Hungarian method from the predicted duals, as opposed to from the duals that I started with. And I'm going to say, again, here's my predicted duals. Find the min cost perfect match. Find the matching along the tight edges, and repeat. Right? The first issue that you run into is this feasibility issue. Right? So the Hungarian algorithm always maintains dual feasibility. So the duals that you have, the yi's in that algorithm, are always feasible for the LP. But here I might, because predictions go crazy, and you can never trust machine learning, the sum of the y hats could be larger than the cost of an edge. And now this is something that regular vanilla Hungarian algorithm would never have experienced. Right? And this is something that I need to do and something that I need to adjust to. So what are we going to do? The obvious thing to do is to say, well, you want to modify this. You want to minimally reduce your y hats because now they're too big to attain feasibility. right? Again, this is not a hard combinatorial problem of how do you do this. But the thing that makes it tricky for us is that we have to do it quickly, right? Again, we're competing with this relatively fast algorithm on the running times. And so we can't take quadratic or cubic time to say, oh, this is the best way for me to reduce the y hats to something feasible, because then what am I doing? I should have run the original algorithm to begin with, right? So how do we make the dual feasible? You can write down the LP for the actual problem that we're trying to solve here. And again, what are you trying to do? We're trying to minimize the values, these offsets, deltas that I'm going to have, subject to that they should cover how much I am over on any particular edge. So this is a relatively simple thing to write down. And if you think about this for a second, there's a really simple greedy algorithm. And the greedy algorithm is going to work in the following way. It's going to say, I'm going to pick any vertex. I'm going to say, OK, this vertex, of course, has a bunch of different edges that are adjacent to it. How much do I need to change the value, the prediction on this vertex in order to make sure that all of its adjacent edges are satisfied and no longer cause a constraint and no longer infeasible? I'm going to pick that particular value for delta. I'm going to adjust my y hat. I'm going to reduce it by this amount. I'm going to remove this vertex from the graph because now it's only part of feasible subsets. And I'm going to repeat. Right? In particular, this is a linear time algorithm. I'm touching every vertex once, and I'm touching every edge once that it's incident on. And it's easy. It's relatively easy to show that the solution gives you a 2 approximation for what we're trying to find. So what does this mean overall? I'm not finding the best projection from the infeasible duals that I predicted to the feasible duals that I want in order to run the Hungarian algorithm, but I'm finding one that's approximately optimal, and I'm doing it quickly. Right, so I'm trading off speed for approximation here. OK, great. So feasibility, I'm going to round the predicted duals, the hats, into the feasible ones, which I'm going to call the primes. Right, and the optimization now is going to say exactly what we had in mind this whole time. I've just run the Hungarian algorithm starting from these larger duals. I don't start at 0. And what I can show relatively easy, right, is that if y star is the optimal dual vector for this instance, and each one of these iterations of the Hungarian is going to bring you the y primes closer to the y star, the number of iterations is bounded by the L1 norm between these two vectors. Right? You can probably get an even tighter bound in some special cases, but this is going to be good enough for us. Right, so now I have these 3 steps. The thing that remains is learnability. I'm not going to talk about it here. We have it in the preprint, but you can show that learning these duals in particular has a relatively small sample complexity. So you should be able to do it quickly. Right, and so now we can put this all together and we can say, what is our approach? Our approach is I have a lot of these min-cost perfect matching problems. I'm going to somehow obtain these predicted duals. Maybe I learn them. Maybe I use the ones from yesterday. Maybe somebody gives them to me. However I want to do it. Given a new instance, I'm going to project these predicted duals down to something feasible. And then I'm going to run the vanilla Hungarian method starting with these projected down duals. Right. And the theorem that ties all of this together says the running time now is exactly the error that I have between my predicted duals, the y hats, and the optimal ones for the particular instance. So this is the y star times the number of iterations of min-cost of mass cardinality matching. So when this error is small, I can get below this log C state-of-the-art kind of approaches. When the error is large, the error is going to be large, but in the end, what am I doing? I'm running the Hungarian algorithm over it. And so it's, in the worst case, I'm going to start with all zeros. And so it's no worse than not taking your predictions into account. And as I've mentioned, but didn't show you a proof, that the number of samples that you need to learn here, we can bound by O tilde about n cubed. So n cubed is not ideal, but I think the main message here is that it's polynomial. It's not an exponential number of samples that you need in order to learn these reasonable duals for your problem.
Sergei,
right? Yes.
We have a question in the chat. So Kostas asks, are you using the features of the graph to compute the predicted y's?
So if you're doing this in practice, yes, you would essentially say, there's every node has a feature associated with it. Maybe if we're scheduling, you can say these are jobs, these are machines. Some of these machines are large and have large capacity. Some of these jobs maybe emanate from different parts of the system or different organization or whatever. And so those will be the features that you use to learn the whys. Exactly.
Thank you.
Other questions? Okay, so does this work, right? So I can tell you a nice story about how this kind of formalizes primal-dual, and this gives you an idea of doing this better than the Hungarian method. But let's see, right? So the first set of experiments we're going to run is going to be on synthetic data to really understand the different trade-offs that are going on here. And so what we're going to do is we're going to start with a large bipartite graph. We're going to plant a min-cost perfect matching in it. And we're going to generate new instances of this problem by adding random noise to the edges of this bipartite graph. And this random noise is mean zero, but is going to start increasing the variance. And so as you increase the amount of noise, you slowly destroy the planted matching that you have, because of course some new edges are going to come online, and these new edges might have noise that's largely negative, and so they should be part of a new min-cost perfect matching, and so on, right? But this allows me to control kind of the variance of the noise to say, is this a perfect prediction versus there's an error in the prediction? And now look at the running time. Here I'm plotting iteration cost, but I can also look at the running time. So here on the y-axis, I have the iteration count, the number of steps of Hungarian method that I need to do. On the x-axis is this extra noise that I'm adding, normalized by the original weight of the edges. So as I move to the right, I'm adding more and more noise. So things are becoming more and more unpredictable overall. And in orange, or on the bottom, as you would expect, is the learned duals approach. And on the top in blue is the Hungarian method. Right. So you do see that if there's something to learn here and the noise is relatively low, the learning approach dominates. What I can go to in the next step is to say, well, let me just expand the scale of this graph. And I'm going to say now I'm going to add a lot more noise overall. And you see these two lines converge, right? And what these two lines converging really means is that now from this point, there's nothing to do. There's nothing to learn. The instance really is random. And as I add more and more noise, this does plateau in the end. The instance becomes just to say, here's a new random instance. Can you find the min-cost perfect matching on it? And of course, there's not, you shouldn't expect to have any gains, right? So when the noise is high, there's nothing to be learned. So you converge to what you have. Great. We can do this now. This was a synthetic data set. You can now do this to derive this from real data sets. The kind of how do you derive perfect matching problems from a geometric data set is an interesting question in and of itself. But the punchline remains that sometimes the learning gains, even on real data and non-synthetic data, can be quite substantial. So kind of more than 10x reducing the iteration count. And on one hand, this shouldn't be surprising, right? If there is something to be learned, what we found is here's a way to exploit the fact that these instances come from some constrained distribution. And the last one is the learnability question, right? And we all know that kind of the packed learning bounds that we get are usually the worst case correct bounds, but are quite pessimistic in practice. And so here we're looking again at one of these geometric instances, and on the x-axis, what I'm plotting is the number of instances in the training data, so to speak, in order for you to predict the learned duals. And on the y-axis, again, is the iteration count. So the way to read this is that as I go from left to right, I get a better and better prediction of what's going to happen next. And again, the orange line is the learned duals. And so it starts out in the same place as the regular Hungarian method. If I don't have anything to predict, there's not much I can do. But as I move forward and I get a little bit of predictions, even after a handful of instances, I can already say this is how the matching should look like. This is sort of the meta structure for the matching that I need to find. And of course, this is much lower than the n-cubed bounds that we derived, because this is single or double digits overall. Right. So that's the conclusion, right? So here's to kind of an epilogue. We were able to do this here for matchings, right? And the point is that many problems are solved repeatedly on very similar, almost identical instances day in and day out. Scheduling is especially kind of an easy to understand culprit for this because jobs on machines run every day. You have your backup jobs, you have your update jobs to update your web search index, or you're backing up user data or something else. And these are run relatively predictable. They're not exactly the same because sometimes somebody tries a new way of doing backup, or some job dies in the middle, or it hits something. And so it doesn't arrive at exactly at midnight, but it arrives at 12:10. And so you need a little bit of robustness in terms of how you're doing these predictions. And so what we want to do is to take advantage of these frameworks to say, this is how we use this warm start, that we should look at the duals, for example, instead of the primals, in order to use this to our advantage. Right. And the challenges that I think I've gone over several times now is really to say, you need to get all three of these. You need to say, here's something that is going to present a good summary. So you need to identify what it is that you're actually predicting, and then somehow say, the thing that I'm predicting is both rich enough in that I can use these predictions effectively to speed up my algorithms, or maybe to get better competitive ratios if you're in online setting. But it's not too complex in that they're pack learnable. So this is the balance. This is the game that you want to play, right? You're not trying to say, oh, I'm going to predict exactly the instance that's going to appear, because that's not going to be learnable, but I'm predicting some structure about the index, about the instance that's relatively sparse. And that sparsity gives me the learnability, but the utility of the structure gives me some way to use these effectively. If I may just to zoom out for a second, I think the other really interesting way to approach these problems, and one of the directions we've been going with this as well, is to say, there's many different ways to go beyond worst case, right? We talk about stochastic input, so it really is drawn from distribution, like in the example I described right now. We talk about problems with random arrival, kind of the secretary problem is the usual example here. There's really interesting work on kind of what I call optimistic analysis, where you assume your data follows a particular distribution, and if your assumption is correct, you get really good results. And if it's incorrect, you get some worst case guarantees. And so you lie somewhere in between. There's these heuristics that I've talked about. And all of these approaches, what they're really doing is that they are constraining the input that's going to come, right? And by somehow saying that by tying this through the lens of predictions, you can actually go ahead and unify a lot of these models by formally saying, well, here's the signal, here's the structure of the signal that you have. And now, stochastic input gives you one way to look about the signal, random arrival gives you another different way about the signal, and so on. And so kind of it really forces you to say, what is the fundamental thing that's going on in this combinatorial problem, and how do I exploit it further? And I'm really excited about this area, as you probably know, and kind of there's a lot of different places where we can use predictions to go beyond worst case analysis. I think there's been a lot of talks this morning and a number of talks yesterday around this as well. And whether it's competitive analysis in online algorithms, whether it's space complexity in streaming algorithms, whether it's running times, all of these can benefit by saying, like, your data is not completely worst case, but it's still unpredictable. And so it allows you to straddle that boundary between being kind of trivial because it's super predictable, or not interesting, not powerful because it's not worst case. And that's it. I'll stop here for more questions.
Thank you. So thank you very much. We actually have a couple of questions that I didn't stop you for because you were already summarizing. So the first is the first is from Murali Narayanswamy, and this question asks, are the learned duals predicted or estimated to be close with MSE or some other loss function?
Right. So okay, if I may rephrase the question to see if I'm answering the right one, is to say, how do you actually learn these duals? Because I told you about the sample complexity, but I didn't tell you how do I get them, right? And so what we find is that just doing exactly as the questioner asked, empirical risk minimization, to say, here's a bunch of different instances. What are the duals that I need to get in order to minimize I think the L1 on the past examples? And these are the duals this is how I'm doing the learning. So the learning process itself here is also relatively simple and easy. It just requires you to solve each instance to optimality, and then you're doing almost an averaging kind of trick.
I see. Great, thanks. And I have this second of 3 questions from Ahmed Sadeghi. Has this problem been studied in the online setting where one of the 2 sets of vertices, along with their incident edges, are coming online to see how the predictions improve the competitive ratio?
Yes, thank you for that question. The problem has been studied a lot in the online setting because in the sense that in the following setting, the fixed vertices are different advertising contracts that people want to serve. And the vertices arriving online are users that are coming in. And so now you have a question that says, Nike wants to show its ad to 100,000 people that satisfies certain demographics. A person arrives and it could be served by Nike, it could be served by REI, it could be served by something else. Which ad should you show to this person, right? So this is an online matching exactly in this realm. And there's a lot of really interesting work on how to do this. Duals play a large role there. Predictions play a large role there. And there's some kind of unexplained questions because it turns out something that's kind of in between formal duals and predictions works really, really well. And we don't have a full-fledged understanding of why. But absolutely, that has been well studied and there's more to be done.
Thank you. And a third question is from Philippe Rigolet. I'll let him ask you.
Yeah, so actually just following up on this point, how is that a matching? I mean, can Nike print this ad on like 20 different people?
So it becomes almost a B matching, and Nike has an upper bound where they say like, we don't want to spend more, every ad costs money and they don't want to blow their advertising budget.
Okay. So, okay, here's my question. So you insist on studying the Hungarian algorithm for this, and there's many other ones. And, so I come from optimal transport. So people are doing a lot of Synchorn, and there's greedy versions of it that you could use. Do those algorithms lack some sort of monotonicity that would allow you to keep the warmth of your warm start? I mean, is that what you take advantage of from the Hungarian algorithm, is that once it's warm, it stays warm?
Right. So I think for those algorithms, I don't know enough details. So it would be interesting to go back and to see, is it easy to adapt this to warm start them as well? And I'll be happy to follow up to learn more myself. But it is the monotonicity here that's actually really key for us, right? Okay. Because you're maintaining dual feasibility by just only raising the y's in Hungarian method.
Okay, and the second question I have is a more learning question associated to this, rather than saying, so when you have IID data, so I wasn't really sure what your learning paradigm was here, since you said I have some sample complexity and then I'm just going to work in terms of like how warm I was to start. Another question you could ask is if my graphs are indeed sampled IID from some model, for example, a planted model that you're describing, a natural question would be to try to upper bound the expected running time, right? So on a yet unseen instance, but from the same distribution, and that could possibly bring out some properties of the distribution that are, either it's nice or it's not nice, and if it has zero variance, then you're good to go. Otherwise, not. Is that something you've looked at all?
It's something that we've looked at empirically, but we haven't looked at it formally. But exactly this question of, how does the variance essentially, the variance due to the distribution that the examples are drawn from in the optimal duals, how much does that play a role in the running time? I think that's the quantity that I would look at. I think that's the quantity that you're getting at. And then can you say that, this is what we've seen in the plot where the 2 lines kind of started out separately and then converged to 1 because that variance got too high, right? So clearly the delta between them as the variance of the sample, as the variance of the instant distribution goes up, your gains should go down. And so we can see that empirically, but formally, I can't make that statement.
Okay. Thank you very much.
Okay, one more question came up, and I see that I've been sending messages to all the attendees, so sorry if they look random. The question is from Kristen Koester. What assumptions are needed for the existence of a good learning target? E.g., does low variance of the input distribution imply low variance of the optimal dual solutions?
So I think this is a related question. There's no assumptions that are necessary here. I think the sample complexity bounds come from analysis that's somewhat similar in spirit to what Ellen talked about yesterday. That's just to say, these are how many, if I change my weights by a little bit, it's unlikely that the algorithm's really instantiation is going to change. The performance is not going to change. It's going to give the same result. And so this is what gives us a bound on the sample complexity, that essentially these things are piecewise linear or piecewise constant in the changes of the duals, right? And so I don't need an assumptions there, but of course, if I have, if it's not learnable because there's the variance of because I'm just giving you random data every single time, then I will learn sorry, let me start from the beginning. The sample complexity bounds tell us nothing about how useful whatever we learn is going to be. It just can say, this is as good as you can learn. And so that question is what we just had a discussion about. Sorry.
Okay, it looks
Can
like.
I ask one question? So is it clear that the Hungarian method would be worse off in a completely random instance? I was a little bit surprised by a graph that even the Hungarian method spent more iterations when the instance was completely random. But a completely random instance seems easier than a worst case instance for the Hungarian method.
It's not clear. So I agree with you that that part about that plot is interesting. Right, and I don't have like a crisp explanation about what's going on there.
So no one has nailed the running. So it would be interesting if someone has nailed the running time of uniformly at random graphs for the Hungarian method. But
right, exactly. That's what this gets to. Yep.
I think there's probably some work by say Mike Steele in the 80s, and then I think Aldous has worked on this. Like they were actually studying, at least the value of the min-cost matching. I don't know if they studied specific algorithms, but I mean, it sounds like it should be something people have looked at. One thing also, it could be that, planting and matching, you're probably doing it in a very simple way, right? I mean, if I were to actually code a planted matching, I would do 1-to-1, 2-to-2, etc. And it could be that the initialization of the Hungarian algorithm is actually very happy with this. And as you're starting adding some noise, then it's not benefiting from the initialization as much.
Right. So, I mean, I didn't want to go into these set of details, but of course, in the Hungarian algorithm, you don't start with all zeros because that's silly. You can at least improve one side directly by raising the y-hats to the minimum edge that's adjacent to it. So you need this tightening. Like that tightening was in all of the examples here, and that's why you see some of the progression some of the speed to be very quick. And maybe it's the role of that tightening that disappears as you increase the variance. Yeah. Sorry, Peter. I'll stop, but I'm happy to talk about it. There's more to be said here, so I'm happy to chat afterwards as well.